Dear students, let us discuss about this topic, theoretical stress concentration. 2 days back we already discussed about this topic, and again we are covering this topic, the theoretical stress concentration factor. Otherwise it is called as geometric stress concentration factor, which is given by capital K suffix T. The T stands for theoretical and capital K is the stress concentration, theoretical stress concentration factor. This is defined as the ratio of maximum stress in a component because of the discontinuity or in the vicinity or in the neighborhood of the discontinuity to the nominal stress at the same section. See, we were discussing about the stress concentration. Stress concentration, because of some hole or something, what happens is in around that hole, stress concentration increases. So that increased stress concentration should be on the numerator, and in the denominator the nominal stress. That means if there was no defect or no hole there, what would have been the stress? That means, if you move away from that hole to some distant place, and there you see, that is called as the nominal stress. So this ratio is called as the theoretical or the stress concentration factor. See, it is given by this formula. Kt is equal to maximum stress upon nominal stress. Maximum stress, if it is, if it is experiencing direct stresses, then it is sigma max upon sigma O. Sigma maximum means it is the maximum stress in the vicinity or in the neighborhood of the discontinuity, and sigma O is the nominal stress that is away from the hole in a distant place. If it is experiencing shear stresses, then it will be tau maximum upon tau O, tau naught. The theoretical stress concentration factor, and this factor Kt depends only upon the geometry of the component, and the material has no effect. It doesn't material, whether it is mild steel or alloy steel, or is it it is some other material. It doesn't matter. You see, this depends only upon the geometry of the component. Geometry means what is the diameter, what is the cross section, whether it is square cross section, rectangular cross section, elliptical cross section, or what is the length, what is the breadth, and such things. Depending upon that, this will be changing. Okay. See, as I told you before, this what KT, where are we going to use it? Actually, it is going to be used in problems at an advanced level when you are computing, when you are designing components on the basis of fatigue loading. But at this level, in diploma level, we are not going to use these formulas for calculating any for designing any component. So at this level, you just know it from the theoretical point of view only. If somebody asks you in the question, what is theoretical stress concentration factor, you should be able to give this. Okay, this is theoretical. You see, when you say theoretical, what is the natural corollary for that? There should be a actual stress concentration factor also. That actual stress concentration factor is called fatigue stress concentration factor. Okay, so in this subsection, we will see fatigue stress concentration factor and notch sensitivity. See, in actual loading, especially in fatigue loading, the effect of stress concentration usually is less than that predicted by the theoretical stress concentration factor. See, stress concentration factor predicted theoretically is more, but in actual practice, what is seen is stress concentration is lesser compared to the theoretical concentration factor. So there is a difference, between the theoretically predicted thing and what is coming actually. Okay, so in design, the stress concentration effect is incorporated by factor known as the fatigue stress concentration factor or actual stress concentration factor instead of the theoretical stress concentration factor. This fatigue concentration factor, stress concentration factor is given by this letter K suffix F. F stands for fatigue, and K F. This is actually actual stress concentration factor. So fatigue stress concentration factor or actual stress concentration factor, that we will be using in design problems and not the theoretical stress concentration factor. Okay, so now which of these two will be more? KT is more or KF will be more? We are saying KT is more, KF is less. So the value of fatigue stress concentration factor KF is lower than KT. So the fatigue stress concentration factor KF, how do you define it now? It is defined as the ratio of actual maximum stress in a component at discontinuity. At discontinuity means what? Why this? What is this discontinuity? It is a crack or hole or any such notch or something. So here in this formula, you see on the numerator, what is there? Actual maximum stress in the notched specimen or in the vicinity of the discontinuity or at discontinuity, you say. You see, in the previous formula, it was theoretical maximum stress concentration factor or simply maximum stress. Okay, here it is actual maximum stress in the notched specimen divided by nominal stress in notch free specimen. Notch free specimen means away from the specimen. It is as good as the same. If there is no hole at all, what will be the stress? That is the nominal stress. Or if you go away from the hole to a distant place in that, so there also the effect of that hole far away is minimal or it is as good as nothing. So that is called as nominal stress. So this is the formula. What is it is defined as the actual, that it is defined as the ratio of actual maximum stress in the component at the discontinuity or in the notched specimen divided by nominal stress in the notch free specimen. Notch or hole or whatever we are saying. Okay, we can, some people may call it as notch free or hole free or defect free or discontinuity free, all these things are same. Okay, so then this is called as the fatigue stress concentration factor. Now we are coming to something called as notch sensitivity. See, what is notch sensitivity? The notch sensitivity, this is used to relate the fatigue stress concentration factor with the theoretical stress concentration factor. That means what? See, that means this notch sensitivity gives an indication how sensitive the material is to the notches or discontinuities. You see, some material may be behaving in one way and another material may be different behaving in another way. We know that every material has its own properties. So if our material that we are going to use for our machine, if that has any notch or any discontinuity, how sensitive is that material uh, to these discontinuities? So this is the this notch sensitivity, this gives the indication. So the notch sensitivity, again the definition of notch sensitivity, you see sometimes they may ask you what define notch sensitivity. So here is the definition. Notch sensitivity is defined as the degree to which a theoretical um, effect of stress concentration is actually reached. That means what we said, KT is more, KF is less. Okay, but KF means the actual stress concentration factor. You see, to the predicted one, how to what degree or to what closeness to KT this KF came. Okay, this notch sensitivity defines that. Okay, here you know this much only. These terms KT, KF and this notch sensitivity, these terms we'll study only from the point of view um, of knowing the terms. Just theoretically, we are not going to use it in solving any problem. Okay, now come to the next point. This is properties of engineering materials. You see, actually you studied mechanical engineering materials, MEM, in the previous or two semesters previously. Okay, now again we are only going to revise these things. You see, materials have various properties. They can be having physical properties, chemical properties, mechanical properties, technological properties, and other properties. Okay, what are physical and chemical properties? You see, the chemical composition. Chemical composition means how much iron is there, how much carbon is there, how much chromium, how much nickel is there, how much magnesium, manganese is there, all those things. To know that, that is the chemical composition. What is the structure, whether it is BCC structure, FCC structure. BCC means body centered cubic, FCC means face centered cubic, and any other type of structure. What structure is there, what is the melting point temperature for different materials, they have different melting points. And what is the thermal conductivity, whether something is an conductor or an insulator, well, if it is a conductor, how much is the conductivity, whether it is as good as copper or silver, or not so much like steel and other things. Okay, coefficient of thermal expansion. So in expand, when we heat it, how much it expands, that is coefficient. So specific weight, what will be its weight per unit volume or something. Then homogeneity, whether it is homogeneous throughout, or in some part some material is more, some part another material is more. All these things come under chemical and physical and chemical properties. Then we come to something called as mechanical properties. Mechanical properties, these are the properties most important for our design point of view. You see, like strength, hardness, ductility, malleability, hardness, elasticity, plasticity, resilience, creep, etc. So all these properties come under mechanical properties. So we will deal with this in a more detailed way. And then there is something called as technological properties. These properties are related with cost. How cost, whether something is costly or cheap. Then what is the machinability, what is the weldability. Machinability means can you machine it proper easily, or if machining is difficult. Weldability, whether weldability, here spelling is mistake, weldability, unnecessarily they have put an here. Okay, weldability, whether we can weld it or not, all and other properties like this. These are the properties which are called as technological properties. So the selection of materials for optimum design. Optimum means just right design. It is important to have a complete knowledge about the properties, mechanical properties and technological properties, because these properties decide the dimensions, physical dimensions of the machine element, or the component for the manufacturing process to be and the manufacturing process to be used for the production of machine element. So if you are, if you have decided in your heart, tomorrow when I go and work in the company, I'll be a machine designer. So then you should be having all thorough knowledge about all the properties of the materials. Which property? See, if some tailor is there who stitches clothes, okay, he should be knowing about the cloth and other things, which cloth is good, which cloth is bad, which shrinks, which doesn't shrink, how some material should be cut, whether something should be washed and stitched, something without washing we can stitch. All those things that person should know. If there is a cobbler, that means one who makes shoes and all, he should know about the material of the shoe, whether the how a leather works, which type of leather, how it expands, contracts, and how gives its shyness, smoothness, and whether it can take stitches, how far it will take the stitches, and whether the holes will be will expand, or whether it doesn't don't expand, and all those things. If any trade you go, you have to know about all those things. If you are a pantela fellow, you should be knowing about all the things, the ingredients that goes into making a pan. Okay, like that, if you are a machine designer, you should be knowing the thorough, you should be having complete knowledge about the mechanical properties and the technological properties, uh, because then only you'll be able to make a right decision regarding which type of material you should use for making your machine. Okay. Okay, Now coming to the mechanical properties, let's see other properties like physical properties, chemical properties, technological properties. When we're not going to study, we will be studying about the mechanical properties. The mechanical properties are those which describe the behavior of the material when subjected to various types of forces and loads. See, this is the definition. If somebody says what is the mechanical property, mechanical property means some external force is coming, some load is coming, some stresses are induced, how that material is going to behave, you know the properties that describe these types of things are called as mechanical properties. A good knowledge of mechanical properties allows the engineer to determine the size and shape of the machine component. You see how thick, if you are making a shaft, what should be the diameter, whether it should be 50 mm, 40 mm, 30 mm, or whether it should be circular, whether it's square cross section, rectangular cross section, I cross section, T cross section, L cross section, or what type of cross section. All these things for determining, you should know about the mechanical properties. Okay, some mechanical properties are discussed below. Okay, so what are the properties? Various properties. Strength is the first one that we study. Strength means, here it is given as a static strength. Okay, so static strength means what? Static strength. To know static strength, you should know what is static load. Static load is that load which doesn't change with time. You see, if any load is not changing, it is constant, 1 kg is 1 kg, then it is called as static load. Okay, then what is the static strength? Static strength means how a material can resist the static load. You see, the ability to resist static load, resist static load without failure. That is called as static strength. So this static strength is normally given by yield stress sigma y or ultimate stress sigma u. Okay, sigma y, to which material do we give? Sigma y we give for ductile materials, because if anything goes beyond yield point in ductile material, we consider it to have failed. And brittle material, when we supposed to have failed, it fails at its ultimate point because it doesn't yield. Okay, you remember this. Okay, static strength, the measure of static strength is it's either its yield strength or ultimate strength. Okay, now the next is fatigue strength. This we were talking about yesterday. Fatigue, under fatigue loading, what strength it has is the fatigue strength. See, this is the ability to resist stress. Instead of stress, here it should have been to resist the load without failure under fatigue loading. Okay, the ability to resist without failure under fatigue load. Yeah, you can just remove the stress to the ability to resist without failure under fatigue loading. You see, yesterday I told you that when a material component is subjected to repeated loading, what happens is it is found that even ductile materials are known to fail much below their yield point strength. Okay, so, and it is found that for infinite number of cycles, infinite number means 10 to the power number of cycles, if you keep the load under certain level, it will not fail. Okay, so that value under which the material will not fail, we said that is it is the endurance limit. So the ability to resist load without failure under fatigue loading is fatigue strength. Okay, repeated loading, if it can bear, that it can bear well, then it is has good fatigue strength. Then elasticity, you have studied already, the ability to regain its original shape after the load removal. When a machine component is loaded and the load is removed, and then it is regaining its original shape, then it is called to be elastic. Then next is plasticity. Plasticity means ability to retain permanent deformation after load removal. You see, this material retains its permanent deformation. That means what? If you are loading on the stress strain diagram beyond yield point, if you have gone, then only it will retain its permanent deformation. If you are within the elastic limit, it won't. Okay. So some materials can be easily deformed. Some materials are difficult to deform. Okay. So that is the plasticity. Okay. Then stiffness or rigidity, the ability to resist deformation under load. You see, if there is a cantilever means what? It is supported on one end and free at the other end, so that is called a cantilever. So for example, I am telling a cantilever, it can be simply supported beam also. If we are putting load and it is not bending a little also, that means it is very stiff. A thing that is stiff doesn't bend, that doesn't deform much. Okay, so this is stiffness. Stiffness is the ability of the material that it can resist deformation under load. Then ductility is the property, the ability of the material that can be drawn into wire. You see, like a gold is a good, best example for ductility. With gold, yes, we can, pull it into long, thin wires. Okay, mostly, ductile. Okay, these are all ductile materials have ductility. Our mild steel, our copper, aluminum, these are all ductile materials. Gold is silver; they are all ductile materials. Okay, then we have brittleness. Brittleness means a material is brittle when with a hammer, if it breaks into pieces, it is brittle, like a glass, and like a cast iron. Okay, the ability to rupture with a negligible deformation. Okay, next is malleability. Malleability is the ability to undergo change in shape, in size and shape. Malleability means it is the property of the material by which it can be rolled into thin sheets, or it can be hammered into thin sheets. That is the property called as malleability. So ductility, you can make it into wire. Malleability, you can make it into sheet. Then something called as resilience. Resilience means the capacity to absorb energy when deformed within elastic range. Within elastic range is called resilience, and up to fracture is toughness. Both are same. This is the ability to absorb energy up to the elastic point is resilience. Up to the fracture point is toughness. Okay, if in stress strain diagram, the up to area under the curve up to the elastic point is resilience. The area under the curve up to the fracture point is toughness. Okay, so resilience is the capacity of the material to absorb energy when deformed within elastic range. Toughness is the capacity of the material to absorb energy when deformed up to fracture. Okay, then something called as hardness. Hardness means this is the property which is desirable for all cutting tools and all those things which are subjected to excessive wear. Hardness, wear and tear. Wear means what? Yeah. Wear means what? Every material wears off. Constant using. वो हिंदी में घिस जाता है वो घिसता है कोई चीज, तो घिसना नहीं तो हार्ड होना चाहिए. अगर नरम रहता, सॉफ्ट रहता, तो वो जल्दी जो है ना खत्म हो जाता, घिस जाता है. ओके. Okay, hardness is resistant to penetration. Means what? If you are taking a metal piece and you are pricking it with some pin or something, is there any indentation there? Is the pin going in or something? Is any mark is left? Then it is soft. If it is you cannot make any mark, then it is hard. So it is resistant to penetration. Abrasion means what? If you with a pointed thing, with a stone, if you are if you are making a line on that metal sheet, is it leaving a mark there? Abrasion means what? Sand is coming, sand is flowing. Okay. um, then our two pieces are rubbing against each other, then if the material is being removed, then it has less abrasion, it is not good in abrasion. That means its hardness is less. Then plastic deformation. Okay, more than the plastic deformation, this penetration, abrasion, and indentation. Suppose we are pricking some ball or something against it, charra. हाँ, चर्रा को ऐसा घुसा देते हैं, उसमें क्या वो कुछ इंप्रेशन गिर रहा है? क्या इंप्रेशन गिरता है तो सॉफ्ट, इंप्रेशन नहीं गिरता तो हार्ड है. So this is the hardness. I told you where this material is important, especially in case of cutting tools. This property is important, hardness. Then creep also we have studied what is creep. And creep is the progressive deformation under constant load for a long duration, maybe at elevated temperatures or high temperatures. This is creep. These are some of the properties, mechanical properties that we have, that we need to keep in mind. Okay. Okay, we stop here today.